All right, hey everyone. We are covering. This is welcome to week 4. Again, this is a weekly review, so we are gonna cover whatever you went over lecture in the past couple of days, including yesterday and the Thursday before. So last week we we talked about nomenclature, about alkane naming. And like priority and like how numbering works. We talked about, isopropyl, sec-butyl, isobutyl, and T-butyl or tert-butyl. Nomenclature will most likely show up on your exam if it already didn't on your quiz. Nomenclature, functional groups, hybridization, sigma and pi bonds can all technically be a part of one compound or structure, or similar questions. So those are kind of more or less standalone questions. Along with resonance is going to be a huge part of your exam too. I'm not sure of the format, whether it's multiple choice or free response. Regardless, it should still be similar in terms of questioning. And then we also went over isomers. We talked about, we went a little bit ahead, talked about enantiomers and diisomers, and I had to like kind of talk about chirality. I'll go over it again today because maybe some lecturers didn't get to it quite yet, but so I'll brief you guys on that. And we went over real quick, we went over IR. So hopefully you guys are good with that, since some of you guys had a quiz over it. If not, we'll cover IR again during exam review next week, right before your exam. All right, so today we're gonna review chirality again. We'll go over chairs, Newman, and Fisher projections. And I think that should be everything that's on your exam. If not, whatever we don't get to finish, we'll cover next week. All right, so let me get into, and ignore the chapter numbers if it doesn't line up. All right, so real quick, we're gonna talk about chirality again. So in chirality, you have a carbon and 4 different groups. Okay, so this is group 1, group 2, group 3, group 4. Okay, so this is again a chiral carbon. Okay, and most of chirality is gonna, if not all, is gonna deal with carbons. I haven't dealt with a atom that's chiral other than carbon, so don't worry about any other atom, because carbon is usually the one that has 4 bonds. And each of these 1, 2, 3, and 4 are not equal. They're all 4 different unique groups. And notice I said groups instead of atoms because you could have something like this, where even though this carbon is bonded to other carbons, it's still different because these are different groups. This is a methyl, this is an ethyl, propyl, this is a pentyl, but yeah. Yeah, so the point is, even though the first atom might be the same, you have to look at the entire group by itself. So each of these are going to be completely different. All right, again, so how we number these, we're going to look at weight. So number by atomic mass. Okay, so let's say I have a carbon that has bromine here, a methyl group on my wedge, and a hydrogen on my dash, and then let's say we have a alcohol over there. So I would number, so I'm going to look at whatever's directly attached to this chiral carbon. And we identified it's a chiral carbon because all 4 substituents are unique. So bromine is obviously going to be the heaviest atom. And then for alcohol, we're looking at the oxygen first and not OH as a unit. And then here we're looking at CH3, even though it's not written. Just remember that's a CH3, and then here we're looking at a basic hydrogen. So right off the bat, we can identify that this is hydrogen is going to be number 4, and then bromine is going to be number 1. Because bromine is heavier, and for that you just need to look at your periodic table. Then it's going to be oxygen, and then our methyl group. Okay. So to look at the direction, there's something called R and S. So R is going to be clockwise, and S is going to be counterclockwise. Okay, and this is the direction your groups are heading towards. So to find that out, you have to look at your number 1 and number 2 and draw an arrow from 1 to 2. And it doesn't matter that 4 is before 3, as long as 1 is going in the direction to 2, it works out. And obviously, 1 can also go around this direction, but we're obviously looking for the shortest distance. So in this scenario, in this example, it's going to be this chiral carbon is going to be R. Okay? And that's most of what you have to know about chirality. Really, you're just looking at different groups and their weight. Obviously, when in this scenario, when they're similar, you have to go by atom, and the first point of difference is what will tell you. Like, even, let's see. Okay. Let me give you guys an example. So let's say I have something like this, and I have a bromine all the way here, and let's say this is on a dash, and I have a wedge hydrogen. If I were to number this, so I'm going to put 4 here. I have a T-butyl. So I have a carbon, 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 right? So I can't figure anything out. I'm going to look at what this carbon is bonded to, which has to be 3 other things, right? So this bottom one is bonded to 3 hydrogens. Okay? This bottom right one is bonded to 3 carbons. Okay? So obviously between bottom right and bottom right is going to be better. So this top one is bonded to 1 carbon and 2 hydrogens. Okay? Now, even though there's a bromine, and even though this whole group looks bigger, or it is technically bigger, you have to look at the first point of difference, okay? Which is going to be this right here, okay? So first point of difference, there's bottom right and top are going to be similar. When we look at second point of difference, bottom right has the heavier atom. So this is going to be our number 1. This is going to be our number 2, and this is going to be our number 3. Okay, and then doing chirality, go 1 to 2. It's going to be counterclockwise, so this is going to be S. Well, it should be S, but our fourth lowest priority group is on a wedge, so it's actually going to be on an R. And I'll explain the different cases for our fourth priority group. But what I was trying to explain here is you don't always look at the biggest group. In this scenario, bromine would be the biggest single atom, but again, we have to look at each individual point of atom to look at priority.
Wait, how did you know that the number 2 has C, had a carbon?
So this is our chiral carbon, right? So this carbon is bonded to this carbon here, this carbon, and this carbon, right? And then this carbon is bonded to this carbon, but it's also bonded to 2 other hydrogens. Was that your question?
Yeah.
Okay. And then this bottom one is bonded to 3 other carbons. That's why this one was number 1 and this was number 2, regardless of bromine. All right. So now we're going to look into different scenarios where our fourth group is on a dash, on a wedge, and on a line. So this is going to be our dash example, this is going to be our wedge example, and this is going to be our line example. Okay. And I'm going to try to use the same example. So let's say I have bromine. Okay, so let's say one of that is an ethyl and one of this is a methyl. Right? So let me draw out all the scenarios and then we'll talk about it. Okay, so in scenario 1, our fourth priority group is on a dash. So if it's on a dash, we keep the chirality. Okay, so let's quickly do the chirality. Bromine 1, ethyl 2, methyl 3. It's going to be clockwise, so it's going to be R. So if it's R, it stays as a R. If it's a wedge, we always flip the chirality. So if it's R, it's going to be S. If it's S, it's going to be R. But again, let's do the chirality again. So this is 1, this is 2, this is 3, this is 4. So it's going clockwise. So this should be clockwise is R, but because our fourth group is on a wedge, it's going to be actually a S. And then if it's on a line, we have to get our hydrogen, rotate the molecule so that the hydrogen is either on a dash or a wedge. If it's on a dash, we can keep it. If it's on a wedge, we flip it. And we can rotate as many times as we want, but it's easier just to rotate it once to either a dash or a wedge. So real quick, if we don't do any flips, I'll explain what the chirality would be. So this is 1, 2, 3, 4. In this scenario, you might be confused which way to go if 1 and 2 are directly across from each other, because looking at it, this could be equal direction, but it would make sense to go clockwise because the 3 is right after 2. So we're going to go this way instead. Okay, so if we go that way, it's clockwise. It's going to be R. But again, because our hydrogen is on a line, we have to rotate this. So how we rotate this is we're only rotating 3 bonds. And we're gonna keep, let's see. Okay. Yeah, so we're gonna keep this structure the same, and so the stereochemistry is gonna stay the same. We're just rotating along this ethyl group. So think of like having 3 pens or pencils, and think of this as like your arm, okay? So this is your arm, and think of the carbon as, your hand, okay? And think of each of these as, pencils, okay? So the stereochemistry stays the same, but we want our hydrogen to go to a wedge or a dash, and wedge is like right next to each other, so we're going to do the wedge version. Okay, so I'm going to redraw this so you guys can see. So if my hydrogen goes over there, it's now going to be on a wedge, and my bromine moves over to the dash. I'm sorry if this is too small. And then my methyl is going to go down to my line. Okay? And again, we still keep the same thing because, again, it's rotating like on a single bond because single bonds have rotational symmetry. Okay? So now in this scenario, we have bromine 1, ethyl 2, methyl 3, and then hydrogen 4. It goes counterclockwise. So this is S, but because our 4th group is on a wedge, it goes back to R. So sometimes even if you don't flip it, it's still the same. But sometimes when you do, not flip it, when you do rotate it, sometimes this isn't the same as not rotating it. So regardless of what chirality you get here, I recommend always rotating it to get your hydrogen or whatever your 4th lowest group is on a dash or a wedge. Yeah. So any questions so far? Do you have any questions? Okay. All right. So again, that is important for chirality. One sec. Fresh. Okay. That is important for chirality because it goes into your isomers. So real quick, we'll talk about enantiomers and diastomers. And I briefly mentioned this already last week. So let's say you have compound 1 and compound 2. This is going to be for enantiomer. Okay. And then let's say carbon 1 or structure 1 has 3 chiral carbons, and you have R, R, R. Structure 2 is going to have S, S, S in order for this to be an enantiomer. Okay? It's going to be the exact opposite or a mirror image. Okay? So I'll give an example, and maybe you might have seen this already. But if I have a bromine that's on a wedge there, and I have a bromine that's on a dash, and I'm comparing this to this. Okay, so notice how it looks like a mirror image, or it's like flipping over. If you take this, if you put like a mirror right here, and you flip it on that side, you should get this image right here. All right, so that's an enantiomer. For a diastereomer, you have structure 1, you have structure 2. This is for diastereomer. If your structure 1 has 3 R's, as long as one of the chiral carbons flips, it's going to be a diastereomer. It has to be at least one, and obviously not all of them, because then it's going to be an enantiomer. Okay? So again, you have to know chirality in order to answer any isomer questions, especially regarding enantiomer and diastereomer, as well as a identical, because isomers have the same chemical formula, but depending on how they're structured, because sometimes they might have the same chiral carbon. So let's say you have 1, 2. In order for it to be identical, it's going to have the same chirality. Okay? So in those scenarios, you choose identical. All right, so if there's any questions, let me know on that. Otherwise, I'm going to quickly kind of showcase all of the previous work so far. Just make sure to, for the line, it's going to be rotate. So you can either keep, flip, or rotate for the 4th priority group. Okay. All right. So now we're going to talk about chairs. Okay. So chairs, all chairs are derived from a cyclohexane. Okay. Not a benzene ring, but a cyclohexane. And they have to have 6 carbons. You can have a cyclopentane or a cyclobutane, but those are called something else, like half boats and boats, and all sorts of things. So we have 1, 2, 3, 4, 5, 6. And then when we draw our chair, you can draw it in different ways, but this is how I like to draw it. Okay, where I like to keep my carbon 1 there, carbon 2, 3, 4, 5, 6. Okay, so whatever group you assign 1 here, it's going to be the 1 on the same direction. Sometimes, and usually you want to put your bulkiest group on carbon 1 or whatever equatorial position you decide to. Because your bulkiest group could be on carbon 2. That doesn't necessarily mean you need to put it here. I mean, you can put it here, just put it in the equatorial position. But to keep it consistent, I would recommend always starting 1 here or whatever way you prefer. Okay? All right. So we are going to look at each of the positions. So whenever you're putting substituents and transferring it to a chair, you can either put it in a bent way, which is called So these are all the bent directions. Okay. So we abbreviate it with E. And then the straight way is called axial. So it's just straight up and down. Okay. So this is, you can use this as like a template. I recommend you write this like in your notes somewhere so you can always refer back to this. All right, so let's think about how we determine if it's going to be equatorial or axial. Okay, and actually I can write it here. So there is a template that I use, and I'm not sure. I learned it from previous upperclassmen, and I'm not sure if this is taught in lecture or elsewhere, but this is how it makes sense to me, and it works for me. So let's say you have this template. If it's all wedges, if it's all the same stereochemistry, you're gonna alternate in your directionality. So, so this is gonna be equatorial. So it's gonna alternate, and then here it's gonna be our axial. Okay. So let's apply that logic to like an example. Let's see if I can zoom out. Okay. Try to keep that in the picture. So let's say I have a T-butyl, which is on a wedge, and let's say I have a methyl there and a methyl there. Okay. So if I were to transform this into a chair, not the prettiest chair, but yeah. So again, I'm gonna label my carbons. So this is carbon 1, 3, 5 is gonna be carbon 1, 3, 5. Okay. So I always want my bulkiest group so bulkiest, I don't think I spelled it right, but bulkiest, just erase that, group. So always place it in equilateral position, because the whole reason for this is to avoid electron clouds. So whenever you have a bulky group clashing with other substituents, their electron clouds are going to mesh with each other. And this is very apparent whenever you do, whenever you have a model kit and you're trying to recreate this chair structure or cyclohexane structure. You'll notice that if you put your bulky group in the same direction, whether that's, you know, a wedge or a dash, or like right next to each other, they're gonna like clash together. And of course, that clashing is very creates instability, and it makes the group unstable. Okay, so we could avoid that instability by placing it in a very unique direction. So we are choosing to make that carbon 1, and we are choosing to put that wedge on in an equilateral position. So this would go right here. And again, we don't have to put wedges and dashes on our chair. We can just use line angle. All right, so I was able to put my wedge in equilateral position because I chose it to be. That's why I made this carbon 1. So if I made this carbon 1 and I have to look at carbon 3 and 5, so I have dashes, but my template has wedges. So in that scenario, instead of doing equilateral, I'm going to do axial for these positions. Okay? And notice how that isn't very stable because we have these methyl groups, facing the same direction. So this is, so anytime that clashes, it's called steric hindrance. Okay, and this is a terminology you guys will use a lot in this unit as well as the second unit. Okay. So whenever they're talking about stereochemistry, they're talking about wedges and dashes and like the direction, if it goes into the page or out of the page. And then whenever they're talking about steric hindrance, that's when you have electron clouds clashing into each other. And real quick, even though I didn't really talk about this, this is a wedge. And it also means, so it could mean two things. It can mean towards you or out of the page. Okay, and you have a dash. So this is a dash. This means away from you. And it means into the page. Okay? So wedges and dashes don't necessarily equal axial or equatorial. So this does not equal axial or equatorial, and neither does dash. Okay? So don't automatically assume wedge means axial or dash means axial. It doesn't work that way. Wedge will mean towards you or out of the page, and dash does mean away from you or into the page. So let's also look at the direction these are going. Let's see, actually. About 3, 4, 5. Okay, sorry. This should actually point the other way. Oh, okay. Okay, I'm gonna rewrite this. Okay, so there's our T-butyl, which is on carbon 1. So axial is on carbon 3. And then, so my mistake was this was carbon 5, but accidentally put the axial pointing this way, which is wrong because this is supposed to be carbon 6 is the one that points down, not carbon 5. Both carbon 3 and 5 are going to point up. So I wanted to bring attention to the direction these are pointing to. Okay? So notice how, so we'll ignore axial and equatorial for now, and we'll look at the direction and the stereochemistry it was originally at. So this was a wedge, and these two were not equatorial, but these two were dashes. So dashes were facing up, and wedges were facing down, okay? And I'm not sure if that stays universal through any example, but the point is your dashes are going to be in the same direction, and your wedges should be going in the same direction. That doesn't mean axial or equatorial, because you can have a equatorial that's facing up in certain positions, and you can have an axial that's pointing down in certain positions. But just keep your stereochemistry the same orientation on your chair. Okay? All right, any questions so far? You got?
No, can you just get to the, when you wrote out, like, that part?
Yeah. All right. Let's see. Let me do another example. Just gonna scroll down a little bit. Okay. So I'm gonna give a couple examples, and I want you guys to kind of tell me what, or we can make this into a ranking question. What is, you might have seen this example before. So we'll rank it by more in terms of stability.
Isn't it if there's a wedge and a dash, and if the wedge is equatorial, the dash has to be axial?
Wait, say that again?
If the wedge is equatorial, then the dash has to be axial?
The wedge is equatorial, the dash has to be axial.
Like, don't they have to be opposite of each other? Or is that, like, wrong?
You might be right. I just tend to try not to look at like universal rules like that, because I feel like each molecule is different, so I try to take it one by one. That might be right. I'm not sure. All right. So let's take a look at these 3 examples. Were you done copying this? Were you done copying this?
Yeah.
Okay.
Yeah, I got it.
All right. So looking at these 3 examples, they'll give you like 5 cyclohexanes, and they'll ask you to rank in terms of stability. So the best way is to, change it to a chair and see the directions. And obviously, you're ranking in terms of like the least amount of resistance, which is also known as steric hindrance. Okay, so let's quickly make chairs for it. And usually, if you do it once, you should kind of know for the future. But I would always recommend, even if you know it, to still make a chair just to be sure. All right, so again, these are all methyl groups, so we don't have to worry about like bulkiness or anything. There's a substituent in our top position, so that's always going to be our number 1. So again, going off the template, this is equatorial, this is going to be axial, and if this is equatorial, this is also going to be equatorial, and if this is equatorial, this is also going to be equatorial. And again, I'm using this template where if they're all wedges, and if my problem has, dashes, I simply just flip whatever it is. That red. So again, alternating is going to be equatorial, and then alternating again is going to be axial. Okay, so basically I use this template to go through each of my 5 molecules. So looking at the first one, they're all wedges, so I just simply match whatever equatorial or axial they give me in each position. So carbon 2 is axial, carbon 3 is equatorial, so these 2 are done. Looking at molecule 3 or structure 3, carbon 2 is a dash, but on our template it's a wedge. So again, if it's a dash, we're going to flip axial to equatorial or equatorial to axial. So looking at this, realistically, the more equatorial you have, the easier it is, or the more stable it is. So I'll talk about that later, but just looking at our positions. So I have a methyl in this direction. Let me do all the equatorial positions. Oh, this is not right. Okay, so this should be in the third carbon, and these two should be right here, and then my axial is going to be right here. Okay, so looking off this, I would say this is number 1, and looking off structure 1 and 3, even though I said the more equatorial it's better, you have to look at the distance between this methyl and where it's colliding. So I would actually say I'm actually not too sure, but I still believe equatorial is better, but looking at our chairs, it feels like it contradicts that. But if you take it visually, because if you don't think about it in a chair formation and you think about it like physically, and if you have like model kit, wedge is going up and the carbon right next to it is going down. So it should go in opposite directions. So even though these look like they're colliding, when you have a model kit, you should have the same direction. Or sorry, you should have the opposite direction. But for this, both wedges are going in the same direction. So imagine, putting 2 pencils going up on on a table. Those electron clouds are going to clash next to each other. So even though spatial-wise, this seems closer and to conflict with this a lot more. Like if you think about it visually, the going opposite directions should be better. Which is trans, essentially. And then looking at these two, even though they're both wedges and they're going in the same direction, this is obviously further apart, so this electron cloud isn't going to affect this electron cloud as much as it does in here. Okay? So it might be a little bit subjective, so obviously go whatever your professor recommends. And I might be completely wrong here. This might be 2, this might be 3, just based on like distance. But based on spatial wise and like in my head, this makes more sense. But general rule of thumb is more equatorial you have, the more stable it is. So usually more equatorial equals more stable. Okay? So sometimes they'll ask you to create the most stable product, which is going to be the one that contains more equatorial and more distance away from your bulky groups. And you always want to put the bulkiest group on equatorial. And then when it says most stable or least energy means the same thing. Least stable or most energy also means the same thing. The energy and stability have an inverse relationship. And one other thing, there's something called 1,3 diaxial steric hindrance. And this will kind of explain why you don't want groups in the same direction. So let's say I have a bulky group, and let's say instead of putting it equatorial, I decided to put in axial position. There are hydrogens facing right here, right? So this is the 1,3 is coming from carbon 1 here, and carbon 3 can either go in either direction. Okay? So these hydrogens are going to be colliding with this T beetle or any other bulky group. So in this scenario, if they were facing that way, as opposed to the T beetle this way, there's not going to be as much steric hindrance because it's pointing away from the thing. There's only going to be a steric hindrance between these two because this one is pointing away while this one is pointing kind of close to each other. All right, so it's similar to like everything facing up, like wedges or all dashes facing the same direction. It could get a little bit confusing, so I do recommend sticking with whatever explanation makes sense to you, whether it's me, your professor, a different professor, or some random YouTube, whatever helps you stick with this, stick with that logic, and don't listen to someone else and get confused. So again, whatever makes sense, stick with that. But this is kind of explaining the 1,3 Daxel steric hindrance. Professors might have brought this up already. If not, they might. But this is kind of explaining why equatorial is usually preferred over axial, as well as 1,3 Daxel comes into play in some other moments in OCHEM or OCHEM 2. But yeah, so that's kind of the general gist of chairs. Something else, and I'm not sure if I can draw this properly, but chairs are based off 6-membered rings, but there's something called a bow, which technically is also 6. I'm not sure if I drew this correctly, but basically 6 is obviously greater than 5, which is greater than 4. But these are, membered rings. You guys learned about IR and about ring strain. So the smaller your ring is, the more energy it takes to break those bonds. So energy increases the smaller your ring gets, okay? So that same logic kind of applies to chairs as well. 6 is going to be the most stable ring. All right, so now let's look at Newman projections. And I think we'll only have time for Newman and not Fisher. We'll get to Fisher next week. So let's say, so any Newman projection and even Fisher projection, you're going to have 2 central carbons, which are going to be labeled as carbon 2 or carbon 3 or some other notion. So let's say this is carbon 2 and this is carbon 3. And just to keep it a little bit different, I'm going to put bromine on this one. So each CH2 or each of the middle carbons always has a wedge, a dash, and a line substituent. So for now, we're going to make all of these lines. Okay? And you're always going to have some information on which direction you're looking at. Okay? And professors also draw this little eye either to the left or to the right of your structure. In this scenario, we have carbon 2, which is C2, and carbon 3. And you're looking from left side, meaning carbon 2 is your front carbon, okay? So this, we're going from a line angle to a Newman projection. So for Newman, you draw one big circle. This is going to be your back carbon, and then a dot, which is going to be your front carbon, okay? So the dot, if you notice, looking at C2, this looks like a, right side Y, while this looks like a upside down Y, okay? So we are going to put bonds in a regular Y shape, and we're going to put a upside down Y bonded to the back carbon. Okay, so that is one orientation. You could technically have, so let's say my orientation looks like this. Where I'm still looking from this direction. Then my circle would look like this. And so there is a slight difference, and I'm not sure, again, I don't know what the format is going to be, but regardless, maybe this might be helpful in determining your answer. All right, so there are 3 regions to pay attention to, which is the left side, the middle, and the right side. So the middle is always going to be your lines, and the right and left are going to be your wedges and dashes. Okay, so let's put our line structures already. So again, the back carbon is C3. It's bonded to bromine, so it goes right here.
Can you move it down a little bit?
Yeah. I don't know if I can zoom out, but is that good?
Yeah, that's good.
Okay. So, and then the front carbon is bonded to a methyl group, so I'm just going to put a CH3. And then now we have to determine which side the H's go. And in this scenario, it doesn't matter because they're all H's. So I'm going to put all H's, but sometimes you'll have unique groups, in which case you will have to know which side. So imagine you're looking at this, horizontally, and you're looking from the left side. So if you're looking from the left side, let's say, so if you're, live recording this or watching this or watching it on YouTube, hold up a pencil or a pen, and when you're looking at the left side, go to the left side and point it this way. And remember how wedges go into the page? So wedges are always going to be, if you're looking at it from the left side, wedges go out of the page, which is going to be on the right side of your point of vision. And dashes are going into the page, which should be dashes are going to be on the left side, wedges are going to be on the right side in this orientation. So let me fix what I said. So this is going to be wedges, and this is going to be dashes. Okay? So let's say you're looking from the opposite side. So instead of this way, you're looking at it from this way, then dashes would be on the right side and wedges would be on the left side. So Chairs, Newman, and Fisher projections are very challenging spatially. So if you're having trouble with that, I would recommend a model kit or different, explanations from different resources until one sticks, and then when that sticks, stick with that. Otherwise, with different explanations, again, you're going to get confused, just like chairs. But if you can hold up a pen and then understand that dashes go into the page and wedges go out of the page, that will make a little bit more sense to you, or towards you, or away from you, whatever you prefer. Something else that may be simple is wherever the eye is or wherever the point of view is, you can remember that as where the dashes is, because that should stay consistent. So notice in the original problem we're looking at from the left side, so we're reading from left to right, and the eyes on the left and my dashes are also on the left. And then if we change the problem where the eyes on the right, so if I take this and I put it this way and my dashes go into the page, my dashes is also going to be on the right. So wherever the eye is, that's the side the dash goes, if you want to use that logic. If not, you can use it like as spatially with your model kit. And then of course wedges will go on the opposite side. It is a little bit confusing with dashes and wedges and left and right, so if I kind of fumble my words, sorry about that. But this should be the Newman projection for this example. And I'm going to do one where you don't have all hydrogens. Let's say you have something like this. So you have chlorine here and bromine here. Okay. So notice how bromine is on a dash and chlorine is on a wedge. So automatically you should know that bromine and chlorine should be on opposite sides. And in this scenario, instead of just methyl groups, I put an ethyl on one side and a T-butyl on that side. Regardless, you're always going to have single lines. You're never going to extend your graph or your Newman projection. Instead, well, I believe you can draw it. I'm not sure, but most of the times I've just seen it written out. So for this, it would be a T-butyl. So it would be carbon bonded to 3 methyl groups. So you can write it like that. That's your back carbon. And your front carbon is a CH2, CH3. Okay, so written just like that. All right, so again, my eye is on the left side, so my dashes are going to be on the left. So I see a bromine dash. Let's keep this consistent. So bromine is bonded to my front carbon, so it's on the top left side. And then I have a methyl group right here. And then my wedges on my first carbon, front carbon, I have a methyl group. And then I have a chlorine on my back carbon on my wedge. Okay, so again, these are opposite, so these also have to be opposite. Okay, so that's kind of a good way to check yourself, because that will also stay consistent. So if you're unsure, at the very least, keep bromine and chlorine on opposite sides. All right. Any questions? Okay. All right, so we're almost done. We're gonna wrap up. I'm just gonna quickly talk about the stability of nomenclatures. So there's anti-staggered, which is better than gauche, which is better than eclipse. Okay, so anti-staggered is going to have a 180-degree separation between your 2 bulkiest groups. Gauche is going to have a 60-degree separation from your 2 bulkiest groups. And eclipse is going to have, I believe it's going to be 0 degrees or like right on top of each other. So it's going to be very unstable. So again, or let me draw each of the examples first. Okay, so let's say we have CH3 here. These are all hydrogens. So my two bulkiest groups are exactly 180 degrees away from each other. So there's less steric hindrance, or the least amount of steric hindrance. And then for 60 degrees, my bulky groups are right next to each other. So there's going to be some degree of steric hindrance. And for eclipse, so the back carbon substituents are going to be basically it's going to be on top of each other. It looks like a 15-degree angle, and sometimes, depending on what resource you hear from or learn this, it'll say 0 degrees or 15 degrees, but this is going to be right on top of each other, which there's going to be a lot of steric hindrance. Goes this way, and energy, oh, sorry. Energy increases this way. So this is the most, and this is the most for energy. Okay, so like I said, stability and energy have an inverse relationship. All right, so that's chairs and Newman projection. I think we're gonna stop it there. But yeah, so next week we'll do Fisher projections as well as review all exam material. All right, thank you guys for coming. I'll see you guys next week.